Welcome to the JEE Main 2026 Forever series. So we observed in the previous sessions like sets. Now we are going to observe the relations. Okay, let us observe the relations. In these relations, let us see the main thing I can say before going to the relations. First, we should know the concept of Cartesian product of sets. Okay, first, what is Cartesian product of sets? Let us observe. So I am taking two sets A and B, two non-empty subsets. Then if I take the Cartesian product of A and B, okay, if I take the Cartesian product of A and B, generally it can be denoted by like this A cross B. Okay, this is the Cartesian product of sets. So A cross B is going to be that is you are taking A and B are the two elements which are in A and B respectively, such that okay A belongs to A and small b belongs to capital B. Okay, you are taking A and B two sets, then A B like this. Okay, suppose A is equal to 1, 2, 3. I am taking, and similarly B is equal to x comma y. Okay, then what I get is A cross B is just I am writing all the ordered pairs. Okay, what are those? 1x, 1y, 2x, 2y. So this is nothing but our A cross B. Understand? Very good. Let us observe now the the important properties. What are the important properties of Cartesian product? Okay, A cross B is not equal to B cross A. Why? Because the elements are going to be reversed. Okay, so when the elements are here 1 comma 2, if you take A cross B, suppose you are getting 1 comma 2 is the first ordered pair. Then if you go with B cross A, it's going to be 2 comma 1, right? So ordered pairs, the elements are reversed. Okay, whenever they reverse, the domain and range are going to change. Okay, so that's why A cross B never equal to B cross A. Understand? A cross B never equal to B cross A. Now n of A cross B is equal to n of A, n of B, and n of P of A cross B is equal to 2 times n of A into n of B. Let us take, suppose I am taking a simple thing like this. So I am taking the relation between A and B is R. Okay, R is a relation between A and B. Let me take like that. Okay, so A contains number of elements in A is equal to M. Okay, number of elements in B is equal to N. Let us take. Okay, so how many possible relations between A and B I want to get? Okay, that is going to be 2 power Mn. So what is that? The number of relations, the number of possible relations between A and B is going to be 2 power M and N. Okay, M is where M is number of elements in A and number of elements in B is N, like that. Okay, got it? Yes. Next, N of A is equal to 5 and B is equal to 5, which implies A cross B is node of 5. Very good. If A and B are two non-empty sets and any elements in common, then A cross B and B cross A have n square elements. Okay, A cross B and B cross A have, because both are containing same n elements. Okay, A cross B union C. You see, A cross B union C is equal to A cross B union A cross C. Similarly, A cross B intersection A cross C. Okay, A cross B minus C, A cross B minus A cross C. Okay, like this we can we can check these properties. We can apply these properties. Okay, Cartesian product of more than two sets. Say we took before A and B only two sets. Now I am taking A1, A2, A and so on, up to N. Okay, N sets. Okay, N sets I am taking. So A1 cross A2 cross AN, it's going to be X1, comma X2, so on, Xn, right? Okay, like this you will get. So where I is equal to 1 to 3, Xi till Xi. I is equal to 1 to N. Okay, so if you take two sets, it is going to be tuple, two tuples. and it is going to be 3 tuples, and it is going to be n tuples. Okay, like this we can give the names of Cartesian product of two sets. Next, number of elements in the Cartesian product. Say A and B are two finite sets. Okay, n of A cross B is equal to n of A into n of B. Thus, if A and B have m elements and n elements, and n of A cross B has how many elements? Mn elements. Here I said these are Mn elements, only Mn elements. What I said before, if number of elements in set A is M, number of elements in set B is N, then the number of relations, okay, don't confuse with this. Number of relations, possible relations between A and B is going to be 2 power Mn. That is different, okay? Understand? M into N here, okay? How we proved this? X1, X2, Xn, Y1, Y2, Yn. A cross B you are writing like this. So if you take xm, y1, x2, y2, xm, yn till now. So A cross B has n of A into n of B. That is m into n, or you can take like that. N of A cross B cross C is equal to n of A into n of B into n of C. We can take like that. Okay. These are the relations. You see, these are the number of possible relations, and these are only elements which are present in A cross B. That is very important. Okay. Very good. Let us observe the next one. Representation of Cartesian product. How to represent the Cartesian product? You see, A is equal to 1, 2, 3, B is equal to A. Each element of a set A to each element of set B is represented by how those two are represented. Those two are represented by single arrows, right? Or lines from A to B. So that is called Cartesian product. Okay, representation of Cartesian product by arrow diagram. Okay. Next, so this is about Cartesian product and their properties and their representation. Now, if you go for relation, we know that relation is nothing but it is the any kind of thing between it is happening between two things, right? So two things should be present. No, there are nothing. Those two should not be absent. That is very important. Okay, those two should be present. A and B are two sets. If I take I am taking A and B are two sets. Okay. Then if I take A cross B, okay, any subset of this A cross B, if I take, it defines a relation. What is the meaning? If A cross B, we can write whenever you take A and B, you can easily write A cross B. Okay. And this A cross B, if you take any subset of a subset of A cross B is going to define a relation between A and B. Okay, A to B. Understand? Yes, very good. Next, one more important point I want to say: void relation. The empty set. Okay, the empty set I am taking 5. Okay, 5 if it is subset or equal to A cross B, which is known as empty or void relation between A and B. Empty or void relation we can call. Empty or void relation I can call. Okay, very good. Next, one more important thing is universal relation. What is universal relation? A cross B, if I take A cross B is a subset to itself, right? No doubt, any set is subset to itself. We studied that. So here I am taking A cross B, which is subset to itself. Okay, which is subset to itself. Then I can say that it is universal relation from between A and B. Okay, it is a universal relation between A and B. And one more important thing, that is this is void relation, universal relation, and binary relation. One more important point. Okay, these are the different concepts which are present under relation. Okay, yes. So a relation on the suppose I am taking a relation on the set A to itself. A relation on the set A to itself. It is called a binary relation on A. What do you call it? Binary relation on A. Okay. Yes. Like this, we can observe the different concepts which are related to the relation. So if you want to if you want to define it properly, let us observe the definition of a relation. Okay, how do we define the relation? A and B, you see, A and B are two non-empty sets. Those two must be non-empty. Then only you can make a relation. If it is empty, is it possible to make the relation? No, right? So you take two non-empty sets and R maps A into B is a relation such that A comma B. Okay, this is an ordered pair A comma B. Understand? A comma B such that A comma B belongs to R. In that case, A belongs to A and B belongs to B. So here B is called an image of A. B is called an image of A under relation. You take this is A and this is B. Two sets I am taking. Here A and B. I am making a relation between A and B R. Okay. So this B is called an image of A under relation R. A is called pre-image of B under relation R. Under that relation only we have to specify. Understand? Very good. Yes, let us move to the next part, that is for example, you see, Dasarath, Ram, Bharat, Lakshman, Shatrugn. Okay, so there, this is okay. This is about what I say. Family of Kingdom of Ayodhya. I am taking Kaushalya, Sumitra, Kaikeyi, Urmila, Sita, Madhvi. Okay, and and Shrukriti like this. Okay, you take RH, that is. It is related to B, symbolically written as ARB, right? ARB. It is not necessary to each and every element of set A have to image in a set B. Set B have a pre-image in set A. Okay. It is not necessary that each and every element should have an image here. Okay. It is not the meaning. Okay. Elements of set A having image in B are not necessarily unique. They may not unique. Okay. Number of relations between A and B is the number of subsets of A cross B. That we know, right? Number of subsets of A cross B. So number of relations is equal to number of ways of selecting non-zero subset of A cross B. What is that? You see, number of ways of selecting non-zero subsets of A cross B. So now number of elements of non-zero subsets of A cross B can be written as MnC1 if you take MnC2, so on MnCmn, which is equal to 2 power Mn minus 1. Okay, like this we are getting. So here the very important topic is domain. Before going to the domain, let us observe. Okay, before going to the domain, let me tell you about an interval. What is an interval? First, tell me. An interval is, otherwise, we'll go with the functions. Before functions, we will do that. Okay. Domain. We can go with this. Sorry. Domain of a relation is a collection of elements of the first set participating in the correspondence. You see, I am taking set A and set B. Okay. Set A is 1, 2, 3. Set B is ABC. So it is making a relation R like this. Okay. Here I can call collection of elements of the first set in participating correspondence. Right. It is making, one is making correspondence with A. So one is the domain. 2 is also making in correspondence with 3. 3 is also. So domain is, can I say 1, 2, 3? And before case, Dasharath, Ram, Bharat, and Lakshman, Shatrugna, those are present in the first set. Okay, very good. And in this case, A, B, C, R can be called as codomain. Okay, suppose I have one more element D here. What is that? One more element D. So this can be called as, this is domain. Okay, and this total thing A, B, C, D total elements can be called as codomain. You understand? Codomain. But 1 to 3, 1 to A, 2 to B, 3 to C only. This ABC part only can be called as range. Okay. So range is subset of codomain. Okay. In codomain, because codomain may not have correspondence with before first set. Okay. In codomain, any element may not have any correspondence with the other elements which are present in first set. Okay. Codomain is here ABCD and ABC is only the range. 1, 2, 3 is the domain. Is it clear? Very good. Let us go to the codomain. All elements of any set constitute codomain. All elements of any set constitute codomain irrespective of whether they are related with any element of correspondence or not. I already told you. Okay, we took an example ABCD. ABC are only correspondence with 1, 2, 3. D is not in contact, but the total elements which are present, those are called codomain. Got it? Yes, correct. Next, go to the next one. Range. So range of relation is a set of those elements of set. You see, say I am taking, let me define domain and range perfectly. Or I am taking or is a relation because I took like this, no? AB. This is 1, 2, 3. I took this is ABCD. ABCD. 1, 2, 3 like this. Okay. So I want to define it. Suppose I have or is a relation between A and B. Or is a relation between A and B. Then what I say? How it should be? Then A such that A comma B belongs to R. A such that A comma B belongs to R is called the domain. Right? Is called the domain of R, I can say. Okay. And B such that A comma B belongs to R. You understand? B such that A comma B belongs to R is called the range of R. Okay. This is domain and this is range of R. Understand? Suppose R comma S. If I take R comma S are two relations from A to B. Okay. I am taking R and S are two relations, okay, between A and B. Then, if I can go with R union S, R intersection S, R minus S, these are also relations from A to B. You understand? If you take two relations, their union, intersection, and difference, I can make the relation. You understand? This is very important under domain and range and as well as relation. Okay, got it? Next, very good. This is about domain and range. Next, representation of a relation. So in general set, how we are representing, in the same way we can represent these also, relations. In this form, we have to represent set of all ordered pairs, right? Set of all ordered pairs like A comma B, B comma A, where A belongs to A and B belongs to B like that. And set builder form, the relation is denoted by the rule which correlates the two sets. Okay, that is this is the same as that of sets only, the set builder form. And if you go with arrow diagram means you take like this, you can observe, you can see. So roster form will be -2, 9, -1, 1, like this. Ordered pairs. Okay. Set of all ordered pairs. And set builder form, you know already one condition, basing on one condition, you can make the generalization. A comma B such that A belongs to A and B belongs to B, A less than B like that. And arrow diagram. So through this arrow diagram, this is mapping. Okay. 1 to A and again A to 3 like that. Okay. So this can be called as mapping or arrow diagram. Okay. Now we study the types of relation. Okay. What are the different types of relation? First relation is reflexive relation. So if you take reflexive relation, reflexive, The name itself says, right? So what it says? A relation, suppose I am taking a relation R. Okay. A relation R on set A or on set A is said to be reflexive if every element of A is related to itself. If every element of A is related to itself, then it is called reflexive. Okay, reflexive relation. Every element of A is related to itself. Okay. Next, this is about reflexive relation. Let us take, for example, A is equal to 1, 2, 3, 4. So, can you write the reflexive relation for this? Yeah, definitely. R is equal to what I can write? 1, comma 1. It is making a relation with itself. You understand? So, this is reflexive relation on A. Understand? Okay. So x or y, x minus y, you take x or y I am taking. So which implies x minus y is an integer, right? Is an integer where R is reflexive relation on Z. I can say reflexive relation on Z. Like that we can say. Yes. Next, identity relation. Now if you see identity relation, suppose I am taking A. A is a non-empty set, okay? Then A comma A such that A belongs to A, okay? A comma A such that A belongs to A is going to be our identity relation. You understand? A comma A such that these two going to be, what I say? This is identity relation, okay? But reflexive relation, every element of A, every element of A, every here it contains more elements. Okay, every element of A is related to itself. Okay, here A be non-empty set, then the relation A comma A belongs to A, then it is going to be identity relation. It is represented by IA or something like that. Okay, IA like that we can represent. Next. Symmetric relation. Okay. If you go for symmetric relation, A, suppose A relation R I am taking. R is a relation, right? On set A. On which set? On set A. R is relation on set A. If it is said to be symmetric, I am taking one ordered pair, A comma B. Okay. Which belongs to R. Then B comma A is also belong to R. Okay, B comma A is also belongs to R. If when if A is related to B, then B is related to A. Understand? Then you can say that that relation can be symmetric. What is symmetric? A comma B belongs to R, B comma A belongs to R. If A or B, then B or if A or B, A is related to B, then B is related to A. Then that relation can be called as symmetric relation. X into Y is said to be symmetric. X comma Y belongs to R, which implies YX is also belongs to R. Identity set I is equal to X comma X such that X belongs to X. But reflexive is said to be reflexive if X or X, you see, X or X for all X. Okay, for all X. Here X comma X belongs to X. Particularly you are saying Y is equal to X. Okay. That means all identity relations are reflexive. But a reflexive may not be identity. Why? Because you take 1, 2, 3, 4. I can write the reflexive relation as 1, 1, 2, 2, 3, 3, 4, 4. Right? We observed this example. But this cannot be an identity relation. Why? You see, all identity relations x comma x. You have to take x comma x such that x belongs to x. Okay, x comma x. I is equal to ordered base are same. Okay, you can take like this. So all identity relations are reflexive, but reflexive are not identity. Okay, got it? Yes, let us observe the next part. Symmetric is done. Next, transitive relation. Okay, a relation, say, R is said to be transitive. When do you say that it is a transitive on one set A? Okay, if it is transitive on set A, X or Y I am taking. Okay, X or Y and also Y or Z. Then, then for all, which implies it is going to be X or Z. Okay, for X comma Y comma Z, these three belongs to A. You understand? A relation or on set A, X or Y and Y or Z, X or Y and Y or Z, then X or Z is going to happen, then XYZ, in that case, XYZ belongs to A. For all values of XYZ belongs to A, you can say that relation is a transitive relation. Okay, right. Every null relation is a symmetric and transitive relation. Every null relation is a symmetric and transitive. No doubt it is symmetric, right? Why null relation? Null relation means nothing. So no doubt these two are going to happen. Every singleton relation. Singleton you take. Any singleton relation is no doubt transitive relation. Right? No doubt transitive relation. And universal and identity relations are reflexive, reflexive, symmetric, as well as transitive. Universal and identity relations are reflexive, symmetric, and transitive. Okay. We know universal relation, identity relation we observed. Okay. Okay. But those are reflexive, symmetric, and as well as transitive. Understand? Yes. Next, anti-symmetric relation. Let A be any set. A relation R on set A is said to be anti-symmetric relation if A comma B belongs to R, A comma B belongs to R, which and B comma A is also belongs to R, which implies A is equal to B. B comma A is also belongs to R, then A is equal to B. So I take R is a relation. Okay. R is a relation on set A. R is a relation on set A. X or Y. Okay. And Y or X. Then X is equal to Y. This is called anti-symmetric. Okay. Anti-symmetric relation. Understand? This is anti-symmetric relation. X or Y and Y or X, X or Y and Y or X, then X is equal to Y. That can be called as symmetric, anti-symmetric relation. Okay, got it? Very good. Next, equivalence relation. What is equivalence relation? A relation R from a set X to Y. That means you take any set which satisfies if and only if it is going to satisfy reflexive, symmetric as well as transitive. Then that relation can be called as equivalence relation. That is equal to equality, similarity, congruence of a triangle, parallelism of lines or equivalence. L is parallel to M. Okay. Reflexive, L is parallel to L. And symmetric, L is parallel to M, M is parallel to L. This is symmetric. This is reflexive. L is parallel to M, M is parallel to N, then L is parallel to N. This is transitive. Okay. Like this we can say different types of relations, equivalence relation. Next, inverse relation. This is very important. You see, if I take relation or is defined from A to B, then inverse relation would be defined from B to A. If R is related from A to B, then, okay, inverse relation is defined from B to A like this. That means R maps A into B. Okay, R maps A into B. That is A or B. Okay, then A belongs to A and B belongs to B. Right? Suppose you take the inverse relation. This is from B to A and B or A and A belongs to A and B belongs to B. You understand? Okay. So if you go with the domain and range, domain here is A. For our relation, domain is A, and for R inverse, domain is B. Okay. And here range is B and range is here A. Okay. That is domain of R is equal to range of R inverse. Okay. Range of R is equal to domain of R inverse. You understand? Okay. That is the meaning. Got it? Domain of R is equal to range of R inverse and the range of R is equal to domain of R inverse. Okay, like this, we can take some examples and we can observe those things. Next topic is function. A function F maps. So, what is the relation? What is the relation? What is the difference between relation and function? You see, there is a lot of difference between relation and function. Okay, you take like what I said before. Just we observed two sets, right? A and B. 1, 2, 3. Let me take one more element for A, B, C, and D. So one is making a relation with it like this. Okay. Let me take like this. Here, in the first set, 4 is left. Yeah, no doubt it is a relation, I can say. No doubt it is a relation. But what about, wait, otherwise, let me take like this. It's a relation. Okay. It's a relation. Yeah, you take this one. Now, I am not using this 4, right? This 4 is not in correspondence with any other element in B. So, whenever the relation, whenever any kind of two sets, the first set can be totally make correspondence with the other things. Otherwise, it may not be a function. Okay. So, how do we define a function first? A function, concept of a function fundamental. Okay, you see, function F maps A into B can be expressed as set of ordered pairs in which each ordered pair is such that first element belongs to A and the second element belongs to B, like that. Okay. First element definitely belongs to A and second element belongs to B. That is, as such a function, F maps A into B considered as a set of ordered pairs A comma F of A, where A belongs to A and F of A is equal to B. You see, F of A is equal to B, which is F is the F image of A. Okay, like that. If you see the definition too, you will get a clear idea. You observe, each element of A is associated with some element of B. You should not leave like this. So it may not be a function. So if it makes a relation, if it makes a correspondence with the another element which is present in B, then definitely it is going to be a function. You understand? All elements should be corresponded in the first set. And each element of A has unique image in B. Unique image. Suppose if you take one A and one B, it is not a set. You understand? One has only one image, that is A only. Two has B only. Three has C only. Four has D only. Unique image in B. So what are the two conditions? The first set, all elements should be associated with some element in the second set. That is first point, first condition for the relation to become a function. Okay, and each element of A should have unique image in B. Okay, unique image. It should not take two images. One is going with A and one is going with B. No, not like that. Okay. Thus a function f from a set A to set B is subset of A cross B in which element belonging to A appears only one ordered pair belonging to F. Hence, a function is a relation, right? A function is a no doubt relation, but relation may or may not be function. Okay. Relation may or may not be function. Understand? You see, by observing this figure, you can easily, every function is a relation. No doubt, it's a function. Okay, it's a function because I used all the elements of set A are corresponding to set B, and each element of set A has only unique image x1, y1, and x2, y1. But it can make like 1, 2, 3, AB, 1A, and this 2 also with A. This 2 also with A, like that. Okay. Next, you see this one. This is not a function. Why? Because this 1, 2, 3, A, B, if I take, I cannot go like this. A, one element has two images here. So this is wrong totally. Okay, it's not a function. One element does not have two images. But a B set one element has two images of A. It's okay. Actually it is not a, it's a domain and it is a range. It's a pre-image and it is image. Okay. All right. Very good. Next you see why it's not a function. You see why it's not a function. You see x3 is having one image with y1. X1 is having, y1 is having two images, and x3 can be, here x5 is not making any relation, no correspondence. That's why you can say it is not a function. Easy way differentiate function from relation. Consider every element of A in a is a guest, and every element of set B is a hosting function at the same time, invited by every element of A. One host, one guest. So any guest comes, that host has to invite her, invite the guest, like that. None of the elements can be two functions simultaneously. So if an element is attending two functions at the same time, then it is just a relation. If an element is attending only one function, then it is said to be a function. Got it? Okay. So when it is a function and when it is not a function. Very good. Now let us observe, by observing the graphs, how do we differentiate? How do we say that the function, whether it is a function or not? So what we said, a element, so this is no doubt x, ordered pair means x coordinate and this is y coordinate. Am I right? So every x coordinate has unique y element. It should not have two y elements. Okay. So y coordinate should be one for each x coordinate. Can you agree? For each x coordinate, if you have one y coordinate, then you can say that it is a function. If it is not like that, then it is not a function. Okay. For that, because with y coordinate is important, right? So for that reason, what I am doing is just I am drawing I am drawing a line parallel to y-axis. I am drawing a line parallel to y-axis like this. So it is touching the curve. This is f of x is our curve, right? So curve at only one point. Yeah, no doubt it is a function. Why? So you take any corresponding at any point on the curve. You take any curve. At any point on the x coordinate, you are getting only single y coordinate. Y1. For x1, you are getting y1. For x2, y2. And for x3, you are getting y3 like that. Okay? Yes. Now you take this example. If I draw a line parallel to it, parallel to the y-axis, because I want to test y only. You see, for x naught, this is a point I am taking. For x naught, I have y1 and again y2 and y3. So if the first element x naught, y1, y2, y3, three corresponding. So no doubt it is not a function. All elements are utilized. First condition is satisfied. But it has three images. No, it's totally wrong. It has unique image. When you take graph, if you draw any line parallel to y-axis, then it has to touch the curve at only one point. Then you can say that it is a function. Otherwise, it is not a function because it is touching at 1, 2, and 3 points. That's why it is not a function. Got it? Very good. Let us move to the next part. So here we can have not only we know x square by s square plus y square by b square is equal to 1. It's a relation, okay, which is a combination of two functions. What are those? We can write the function, no, this one y is equal to, you can make y as what I say, y as subject, and you are getting the plus 1, plus b1, and minus b1. Okay, you are getting two functions, right? Similarly, the equation of parabola is a combination of two functions, right? Y is equal to 1 positive root x and negative root x. Okay, you have two functions like this. Okay, so you can have two functions, okay, like this. And with the next very important topic is domain, codomain, and range. I already told you that domain and codomain and range. Domain, here what is domain? If you take any kind of what I say, any kind of two sets, okay, like what I say, A and B are the two sets, okay. In that two sets, I can say in those two sets, I can say A if domain. Domain means here the set of elements which are present in the first set. Codomain means all the elements which are present in the second set. Okay. And range means the set of elements which are associated with the elements which are present in B. This is called, you see here, this is domain and this is total thing is codomain. Okay, domain with domain, that is called, only these elements are called range. You understand? But this CO, this is not the range because these two are not related. These two are not what I say associated with A. Those are not considered as range. Only these elements are considered as range. You understand? Very good. So domain of F is equal to A such that A belongs to A comma F of A belongs to F. Okay. Range of F is F of A. F of A for all A belongs to A and F of B belongs to B. F of A belongs to B. Okay. It should be noted that range is a subset of codomain, right? Codomain means all the elements. Range is only particular elements. Okay. So codomain is a range is a subset of codomain. If only the rule function is given in the domain of the function is the set of those real numbers where function is defined. If domain of f of x is d1, the domain of g of x is d2, then f of x plus g of x is equal to d1 intersection d2. What is that? Sum of two functions is nothing but their intersection of their domain. Sum of two functions is nothing but intersection of their two domains. Okay. Now let us observe the common functions. Okay. Before going to the common functions, wait, let me take, okay, let me take now, I am taking the very important concept, okay, a concept like intervals, neighborhood, okay, and modulus. Those are very important when you talk about this, what I say function, okay. So you know numbers. So real number system. What's the real number system? Real number system is, you know, different types of natural numbers, whole numbers, integers, real numbers, complex numbers, irrational numbers, rational numbers. Okay, rational numbers comes under that. Okay, like positive z plus and z minus, you know, and q, positive rational numbers, negative rational numbers, irrational numbers. Okay, all those you know. And real numbers means, what are real numbers? Q union Q dash or Q complement, I can say, right? Q union Q complement, that is rational numbers and irrational numbers, those two combinedly gives real numbers. If I go with Q intersection QC, what is Q intersection QC? Think and tell. Rational and irrational. Okay, rational and irrational, which are not rational. Okay, those are called irrational. No, what is the intersection part? It's going to be 5, right? Okay, so rational numbers may be represented in the form of periodic, terminating and non-terminating decimals. We know that. That is a basic concept. We can represent any real number can be in the form of periodic, terminating and non-terminating decimals. Okay, like example, 1 by 2 is equal to 0.5. Okay, and 1 by 3 you take in the same manner, 0.333, so on, right? This is non-terminating and this is terminating. If I go with 1 by 7, what kind of thing you are getting? 0.142 2857. This is bar. Okay, this is, what do you call, this is non-terminating and recurring, I can say, like this. Okay, so numbers, a number, if it is in the form of other numbers also, we can see a plus ib form. What are those called? Complex numbers, right? A plus ib form. So you know, these are the different types of numbers you already know. Okay, next, the very important property I am taking, if A less than or equal to B, then what happens? What is the meaning? Either A less than B or A is equal to B. That is the meaning, right? A less than B or A is equal to B. And A is greater than or equal to B means is also in the same way. A greater than B or A is equal to B. Okay. A less than 0. What is the meaning? A is equal to B. If A greater than B, A is greater than or equal to B means A greater than B or A is equal to B, right? A is equal to B. Very good. A greater than or equal to B. If A less than 0, what happens? In this case, if A less than 0, minus A less than 0, minus A greater than 0, sorry. Right? Whenever you take the sign, whenever you change the sign, if you multiply both sides with a negative sign, then the sign inequality also changes. Okay, this is the main concept here. And then next I want to say about dense property. What is dense property? A dense property means you take any two arbitrary real numbers. There exist infinitely many rational and irrational numbers are going to exist, right? Or between any two real numbers, we have infinitely many real numbers. That is called dense property of real numbers, or dense property you can simply call. Okay. Next, you know properties of real numbers already: closure property, associative, okay, closure property, associative property, existence of identity, and inverse, existence of inverse, inverse, identity, closure, associative, and commutative, commutative, and distributive. Okay, these are the main properties. Closure property means if a one element belongs to R, then if you do any kind of operation with this, okay, a plus g, a plus and a belongs to R, a plus one also belongs to R, then it is a closure. Associative means a comma b comma c I am taking. A plus b plus c is equal to a plus b plus c. Okay, that is associative. A plus b plus c is equal to a plus b plus c. Okay, that is, here a belongs to a comma b belongs to R, then a plus b belongs to R, that is closure. Sorry, a belongs to R, a comma b belongs to R, a plus b belongs to R. Next, if you go for existence of identity, a plus 0 is equal to a plus 0 is equal to 0 plus a is equal to a for all a belongs to R. And existence of inverse, you take, if a belongs to R, then a plus minus a is equal to 0. Minus a plus a is equal to 0. Then a is called additive inverse. If you go with a into 1 by a, then a is multiplicative inverse. 1 by a is multiplicative inverse of a. Okay. And then next, commutative property. You see, a plus b is equal to b plus a. Okay, or a into b is equal to b into a. Okay, those are commutative property. And distributive property, you are using two operations here: a into b plus c is equal to a into b plus a into c. That is, next, the other one, left distributive, this one left distributive. And if you take b plus c dot a is equal to b dot a plus b c dot a. Okay, this is right distributive, left distributive, right distributive properties. And then next, a into b can usually written as ab, right? We know a into b into c, also a into b into c. And properties, main order relations. You take a greater than 0, b greater than 0. Then what happens? A plus b no doubt greater than 0. Hmm? And also ab is also greater than 0. Okay. If I take a greater than b, what is the meaning? A greater than b means a minus b should greater than 0, right? A minus b should greater than 0. If a less than b, a less than b means a minus b less than 0, right? Okay. If I am taking a less than b, a less than b, then what do I write? Suppose I am adding plus c on both sides. A plus c less than b plus c. There is no change at all if c belongs to R, right? And similarly, a greater than b. Also the same thing. A plus c should greater than b plus c. C belongs to R. Okay. And the other one is a less than b. Here, these are the main things you have to observe. A less than b I am taking. If c is greater than 0, then no doubt AC less than BC. Okay. And A greater than B, C greater than 0. C less than 0, if I take A less than B, C less than 0. The same thing. Okay, you will get. Okay. A greater than B, I am taking the other one. A greater than B, C less than 0. What happens? A greater than B, C less than 0. Then AC should be greater than BC or less than. A greater than B I am taking, C less than 0. So it is going to make it total negative, right? So the sign inequality also changes. Okay. If C less than 0, then AC should be less than BC. Okay. AC should be less than BC. When if A greater than B, C less than 0, then AC should be less than BC. C belongs to, or C less than 0, I said no. Other way, I am taking if A lies between 0 and B. A lies between 0 and B. Then what happens? 1 by A greater than 1 by B greater than 0, right? Okay. If I am taking A less than 0 less than B, what does this implies? 1 by A less than 1 by B and 1 by A less than 0 less than 1 by B. Correct? Okay. Very good. This is about the real numbers and then ordered relations like properties involving ordered relations. Okay. Very good. Next, if I want to extend our real number system, I want to extend my real number system. The set of all real numbers, the set of all real numbers together with extended, no? I told extension. Okay, I told extension. That is minus infinity to plus infinity. Right? I am taking. That is or minus infinity, comma, plus infinity. If I take this set, okay, this is called extended real number system. Such that how I am taking these numbers, x minus infinity less than x less than plus infinity. Like that I am taking. Okay. For all x belongs to R. So what is our extended real number system? X lies between minus infinity to plus infinity. That can be called as extended real number system. Extended real number system. Okay. So in this system, what are the different properties we are going to observe? Okay. In extended real number system, say I am taking any point A on a real number line. I am taking a real number line, 1 point. So is when do you say that it is a proper point? If is called a proper point and minus infinite plus infinite or improper point. It is a proper point because you are saying particularly here. What about minus infinite and plus infinite? Is it possible to plot anywhere on this this minus infinite and plus infinite on this real number line? We can't plot it, right? So these are called improper points. Improper points, whereas A is called proper point. You understand? Proper points and improper points. Very important. Proper point is can be plotted exactly at one point of that real number line, whereas improper points are minus infinite and plus infinite. Okay. Let us observe some important properties. Okay, with this improper and no improper points. Okay, say I am taking A here. A plus infinite I am adding. I am adding A to infinite. Definitely I will get infinite because infinite is bigger. For all A belongs to R. Am I right? Right. Next I am taking A plus of minus infinite I am taking. A plus of minus infinite. It is no doubt minus infinite, right? Mm. A into infinite. This is also infinite. When if A greater than 0, it is going to be infinite. If A is less than 0, then it is going to be minus infinite, right? Okay. If A less than 0, it is going to be minus infinite. Similarly, A into minus infinite is going to be minus infinite. Okay. If A greater than 0. You understand? If A greater than 0, it is going to be minus infinite. If A less than 0, why? Because this is going to be negative again. Negative, negative, you will get, right? Okay. If A is less than 0, A into minus infinite becomes positivity. Positive infinite. Why? Because A is also negative. Negative, negative becomes positive. So you are getting positive infinite. Okay. Very good. And now A with if I divide with infinite, I'm getting 0. You know that? And A by minus infinite, this is also 0. Okay. and I am taking with proper in this is proper and improper points. I made the properties. Now I am going with only improper points. Infinite plus infinite, no doubt infinite, right? If I take minus infinite plus minus infinite, what happens? Yeah, no doubt minus infinite. Infinite into infinite, it's infinite. Infinite into minus infinite, it's minus infinite. Minus infinite into plus infinite, it's also minus infinite. Minus infinite into minus infinite, if you take both negative, it should be positive. Hmm? Positive. Next, my plus infinite to the power of infinite, positive. It's also positive infinite. And if I take infinite minus infinite, okay, is it possible to do infinite minus infinite? And minus infinite plus infinite, 0 into infinite, infinite into 0, infinite into 0. Next, plus infinite, plus or minus infinite by plus or minus infinite. Okay. So these are whatever I have written at last. These. These can be indeterminate. We can't find it. Okay. One is plus infinite, another one is minus infinite. Both are balancing. Is it possible to say the answer? No. Okay. Similarly, minus infinite, plus infinite anyway, if you change the order also. And you are multiplying 0 with infinite. It never be. It is an indeterminate form. Don't put 0. Okay. So, a 0 with any number is 0, but except with infinite and minus infinite. We can't define it. This cannot be defined. That is indeterminate. Okay. Cannot be defined uniquely. And any possible definition leads, we can call it as absurd results. Okay, if you give like that. Okay, any number by 0 is nothing but infinite, right? Okay, so these are the proper and improper points. Improper points properties. These are improper points properties, and we observed already before proper and improper combination points properties. Okay, got it? Very good. Let us observe the modulus. That is very important. Modulus. Modulus of a real number. It can also called as absolute value. What it is called? Absolute value. It can be represented like this. Absolute value is defined. Okay. So how do we define this modulus or absolute value? So which is equal to x if x greater than or equal to 0, which is equal to minus x if x less than 0. This is very important thing. So mod x is going to be a maximum value of minus x comma plus x, right? So mod x can be written as plus root x square. Can I write? So I want to calculate mod x is equal to how much? Yeah, 6. Okay. Suppose I gave minus mod 6. It is also 6. Mod 0, 0. Okay. Like this, we can easily write the values of. So, mod x is equal to positive x if x greater than or equal to 0. Mod x is equal to minus x if x is less than 0. Okay, that is very important. And very important properties we have under the mod. Okay, what are the important properties? Let us observe. Mod x. I am taking mod x which is greater than or equal to 0. Okay, mod x greater than or equal to 0. X no doubt belongs to R. Hmm? And mod x is equal to 0 when if and only if x becomes 0. Am I right? Very good. Mod x, mod minus x is equal to x for all x belongs to R. Okay. And I am taking minus mod x less than or equal to x less than or equal to mod x. For all x belongs to R, right? Minus, between minus and positive, it is going to lie. Okay. Similarly, I am taking two numbers, mod x and y. X into y you take. Then what do you get? Mod x into mod y. For all x comma y belongs to R. Okay. Next, for any finite real number, x1, x2, xn, so on, I am taking x1, x2, x so on, xn. So their product is also x1 into x2 into so on, xn. Okay. So that can be written as, pi. Whereas for addition, sigma we are using. For the product, we are going to use pi, right? Pi xk I can tell. Because x1, x2, x3, so on, xn I said no. K is equal to 1 to n. Okay. So this is mod you can take. This value is going to be pi k is equal to 1 to n and then xk mod. Like this we can write. Okay. The modulus of the product of a finite number of real numbers is equal to the product of their moduli. Okay. Product of their moduli. Product of the modulus is equal to product of their each moduli. Okay. Got it? So this is about modulus. And some more important properties, let me tell you few of them. And you can say, I can take mod x minus y less than or equal to mod x plus mod y. Okay. For all x comma y belongs to R. Okay. Similarly, mod of x minus y is greater than or equal to mod x minus mod y. Okay. Mod x minus y greater than or equal to y minus mod x. Okay. This is also important. If mod x less than delta, what is the meaning? So, minus delta less than x less than delta. That is the meaning. So, x lies between minus delta and plus delta. That is the meaning. Understand? Suppose I gave like this mod x minus a less than delta. What is the meaning? A minus delta less than x less than a plus delta. Right? What is the meaning? Actual meaning is x minus a lies between. This is the meaning with respect to this x minus a between positive delta and negative delta. So if you add a plus delta here, a minus delta minus a. So you are getting a minus delta less than x less than a plus delta. Okay. Got it. Hi, bro. Next, 0 less than mod x minus a less than delta. What is the meaning? A minus delta less than x less than a plus delta. That is the meaning. Right? But x should not be a equal to a. X should not be equal to a. Next, variables and constants. Constant has fixed value and variable has changing value, no fixed value. Okay. And absolute constants. So some quantities which have the same value, some quantities which have same value under some circumstances. Let us take 5. Okay. Real numbers are absolute constants, right? So you take pi value. It is showing always the same value, right? So we can also observe some constants like arbitrary constants, right? Y is equal to x plus c. You take. I am taking y is equal to x plus c is called an arbitrary constant. Okay, that means constant when compared to the variables x and y but makes various real values. Okay, it represents a family. It is representing a family of straight lines, right? It's representing a family of straight lines. In that, you see, these two are variables, but C may be some any kind of value we can give. Okay, that is called arbitrary constant. Understood? Suppose I want to find the range of a variable. Range of a variable is nothing but set of all numerical values taken by a variable. That is called range. Okay. Range of a variable may be either finite or infinite, right? It depends upon the given question. Yeah. X be the, let me take example, variable x takes the values 1, minus half, 1 by 3, 1 by 4, so on. Then 1 by 3 is preceding, 1 by 3 preceding value is a preceding value. Minus 1 by 10 succeeding value x. Say 1 by 11, 1 by 12, 1 by 13, so on. So here I can say these are the values of x. Subsequent values of x. Subsequent value of minus 1 by 10. Subsequent values of minus 1 by 10. So because these are here you can see 1 by 3 successively, then here you take these values. These are successively, then 1 by 3 is preceding value. Okay, 1 by 3 is preceding value. Like that. So you are saying preceding and succeeding are successive values like that. That means if you want to define any number, you need preceding and succeeding values. That can be stated by our great topic interval. What is that? Interval. Okay. Now you observe the interval. So interval, first what is an interval? Let us observe. I am taking a subset S. Okay. A subset S of R. S of R. This is a big set, universal set. From this I am taking S is some subset. A subset of R is said to be an interval if A belongs to S, B belongs to S, and X belongs to R in such a way that X should lie between A and B. Okay, where X belongs to S. You see, how do you define an interval? The set. What is the set? How do you write in the set form? X belongs to R. Okay, and A less than or equal to X less than or equal to B. This is our interval. Okay. It can be called as a closed interval. Closed interval means by because we kept equal to sign also. Okay. It can be represented with A comma B. Okay. This is normal interval and this is closed interval. This can be open interval, I can say. Okay. Open interval. How do you represent that in geometrically? Let me take. So this is my graph, real number line. So I want to represent A and B. Closed interval means you have to consider the two things. So like this, it can be closed. If I go with this open interval, this can be called as open interval. It can be denoted like this. X belongs to R, okay, such that, how it will be such that X lies between A and B. This can be open interval. You understand? This can be open interval. This can be, this is the closed interval, this one. X lies between A and B and also equal. Okay. X belongs to R. A less than or equal to X. X less than or equal to B is a closed interval. A less than X less than B is an open interval. Okay. Got it? Very good. Let us go to the next left open, right open, left open interval. So left here you see left it is open and this is closed. Okay. So how do you write this? This is going to be X belongs to R. How I can write this? X belongs to R. Okay. And maps A less than X less than or equal to B. It may be equal to B also. It represents the closed bracket. Okay. Similarly, Right open. Right open means left it is closed, right it is opened. So how do you write? X belongs to R, A less than or equal to X less than B. You understand? In this manner. So how do you represent on the number line these two? Let us observe. The first one, how do you represent? It's an open, no? It's an open. So it is A and it is closed and it should be dot. Okay? Can be taken. That is the meaning. Right open. Next, right open. Left closed. So it is going to be closed. It is going to be open. Okay? This is A and this is B. Here also B. Okay? Got it? Yeah. So this can be called as closed and open interval, left open, right open. You understand? Yeah. Suppose I am giving the small thing like this, a comma infinite. Let me take like this. How do I represent? X, no doubt this is going to be X belongs to R. Very good. X belongs to R. Such that. Uh, no doubt it's closed interval. You can easily write A less than or equal to X. This is less than infinite. It's okay. Understand? This it. Okay. Yes. Similarly, A comma infinite. Okay. Right? How do you represent this? I want to represent this X belongs to R, colon. A is also open, no? A less than X, less than infinite. That's it. Both are open. Okay? Yes. Similarly, you take minus infinite, comma A. Okay? Minus infinite, it's closed interval. Then, how do you represent this? Say, I am taking like this. How do I represent? Minus infinite. Minus infinite means like this you are getting. Okay. And A is closed. I can represent like this. But how do you represent this? X belongs to R, right? Colon. Minus infinite. Actually, here there should not be any closed friend. Minus infinite. Sorry. Okay. Minus infinite less than X less than or equal to A. Because it's I can't say we say that minus infinite and plus infinite are improper points, so we can't place it correctly. They are moving like this in this manner we can represent, but we can't represent this is the minus infinite point, this is the positive infinite point, you can't say. So those are improper point, that's why those are always open interval, not closed interval. Got it? Got it? Very good. Yes. In now these are the intervals. In the case of intervals, you see whatever the things which are present, A and B, those are called end points. What are these called? A infinite, like this we are saying no. A comma B, those are called end points. Okay. The quantity B minus A. If you take B minus A, that is called the length of the interval. Length of interval. Understand? Irrespective of inclusion of A and B. Okay. If you take the subtraction of the B minus A, you are getting their length. Since the length is finite, those are finite intervals or bounded intervals, you can say. If the length is infinite, those are infinite intervals. So the set of all real numbers, or it is it self an is itself an interval, right? Okay. So how it is denoted? Or interval is denoted with minus infinite, comma plus infinite. This is the or interval. Okay. Or interval, any real number interval, you can represent like this. Got it? Very good. Next, the very important point, like neighborhood of a point. NBH, neighborhood of a point. What is that? Neighborhood of a point. Say, I am taking one point, proper point, A belongs to R. Okay? A belongs to R. So I want to represent any kind of neighborhood. I am taking a very small neighborhood. This is A point. Very, very near neighborhood. Neighbor to this A. Okay. That is delta I am taking. If delta greater than 0, then what happens to the open interval? A minus delta, comma, A plus delta. This is going to call it as delta neighborhood of A. You understand? Delta neighborhood of point A. Okay, delta neighborhood of point A. So it is denoted by N delta of A. Okay. A is called center. Okay, delta is called the radius. A is called center and delta is called the radius of the neighborhood. Okay. Yes, how do you represent N delta A is equal to A minus delta comma A plus delta. X belongs to R, A minus delta, X lies between A minus delta and A plus delta. X minus A, what is the meaning? X minus A less than delta. So how do you represent delta neighborhood? X minus A less than delta means what? A minus delta less than X less than A plus delta. Okay. How to represent this on a number line? Let us observe. This is my A point. So this is A plus delta. And this is A minus, sorry, A plus delta is this positive side, no? A minus delta. Okay. A minus delta. Like this we are going to represent. Understand? And this is delta neighborhood. Okay. This is neighborhood, delta neighborhood. The next one important point here is if I take neighborhood delta of A, right? If I remove the set point A, set A, what happens? It can be called as deleted neighborhood point of A, right? Deleted neighborhood point of A. So if I delete the deleted neighborhood, then A minus delta, comma A union A, comma A plus delta, right? A, comma A plus delta. A, comma A plus delta. Okay, right. So how do we represent this? Let me represent this. So this is going to be X belongs to R, no doubt. So 0 less than, because you see 0 less than mod X minus A less than delta. Am I right? 0 deleted neighborhood. Deleted neighborhood means A is going to delete. That's why you are making it a whole. Whenever you represent on the real number line, if you represent a whole like this, 0 like that, it is going to be deleted one. When you represent a thick one, it is to be added. That is the meaning. This is point A. This is deleted neighborhood. Okay. So how do I represent A plus delta this one? This is A minus delta. This is real number line. Okay. Got it? This is deleted neighborhood. So A minus delta comma A, this is left deleted neighborhood. Okay. And this is right deleted neighborhood. Left deleted, right deleted. Okay. So there exist infinitely many neighborhoods for point A. Infinitely many neighborhoods are going to exist. Open interval containing A is a neighborhood of point A. Thus, if you take the set of all real numbers, R itself is a neighborhood of A, right? Okay, itself is a neighborhood of A. Very good. Next, one important concept is, suppose I am taking delta 1, delta 2, so on like this, delta n. Okay, delta n positive real numbers. These are what? Positive real numbers. Okay, then, and also I am taking A belongs to R. What I am taking? A belongs to R. Then, if I take intersection k is equal to 1 to n, then A minus delta K, comma, A plus delta K. What do you call this? What we are going to observe? It is also a delta neighborhood. It is also a neighborhood of the point A or not? Yeah, it is also called the neighborhood of point A. If I take one element x, okay, if x is greater than m, let me take, okay. Here, the set of all real numbers x greater than m, the open interval is going to be m comma infinite is called the m neighborhood. Okay, m neighborhood. You understand? This is m neighborhood of plus infinity, and if you take m neighborhood of minus infinity is minus infinity to m. M neighborhood of minus infinity. Okay. So how do you define? For any, let me write the important 2 points. That is, for any delta greater than 0. I am taking for any delta greater than 0, x belongs to a deleted neighborhood. X belongs to deleted neighborhood of A. Deleted neighborhood of A can be, how do you write that? X belongs to A minus delta, comma A, union A, comma A plus delta. You got it? That means what is the meaning? Deleted neighborhood of A means A minus delta, comma A, union A, comma A plus delta. That means 0 less than mod x minus A less than delta. Less than delta. Sorry, 0 less than x minus a mod less than x delta. Okay. So, for any delta greater than 0, for any delta greater than 0, x deleted neighborhood, okay, of A. Suppose in the same way I am taking for any epsilon greater than 0, why epsilon neighborhood of L? Why epsilon? Why epsilon neighborhood of L? L means length of interval. What is the meaning? How do you say that? Y belongs to L minus epsilon, comma L plus epsilon. Okay. That means, which implies Y minus L mod less than epsilon. Okay. Y minus L less than epsilon. Okay. Understand? This is about neighborhood and deleted neighborhood of the points. If you see the very important point like limit point of a set, okay, limit point of a set. Just I will give the definition of a limit point of a set. Let us observe. Let me take some set A. A is subset of R. From real number set only we are taking. Okay, it is A is subset of R. Okay, I am taking a point, one point I am taking A. Okay. A is said to be limit point of A. I am saying A is said to be limit point of A. If every neighborhood of A contains at least one point of A. At least one point of A other than A other than A, then you can say that A is a limit point of set A. Okay. It follows every neighborhood of A contains infinitely many points of A. Okay. For example, you take 0 is a limit point of a set for this 1, 1 by 2, 1 by 3, 1 by 4, so on, 1 by n, so on, like this it is going. So, where it is going to nearly approach, it approaches to 0, right? So 0 is only the limit point of this set. A set may have more than one limit point also. Not only single limit point. It have more than one limit point. Okay. Every point of, suppose I am taking every point of A comma B. Is a limit point of A comma B? Can I say? Yeah. Because both are included, right? Right. Okay. So this is the main limit point concept. So a set, let A be a subset of R. If a point A is said to be a limit point of the set A, if every neighborhood of small a contains at least one point of A other than A, it should contain at least one point. So here you see all points, but other than A is 0. Okay, other than these is 0. Okay, 0 is the limit point of this set. Okay, every limit point of this set is nothing but this set because these 2 points are included here. Understand? Very good. Let us see. These are about intervals, modulus of a real number, and inequalities, and all about real numbers I covered. Okay, very good. Okay, thank you. Thank you for watching. Bye bye.